Welcome to the problem class. This is online video. Okay, the first question is about justify why the reactivity of the indole and the pyrrole are different. That means indole is orientating C2 while the pyrrole is orientating C2 while indole is orientating C3. Okay, well, as you well know, this is a electrophilic aromatic substitution. We are using a Lewis acid. Okay, and the first step is the attack of our nucleophile, that will be the pyrrole or the indole, towards the Michael acceptor. Okay, this is the first step, and what we generate basically is this intermediate. If it's attacking C2, and we can move this we can stabilize the positive charge that we generate in the ring by moving the electrons. Okay, and then the pair of electrons of the nitrogen can be delocalized there, and what we generate okay, we have these three resonant forms if we attack C2. If we attack C3, we generate this intermediate, where we only have two resonant forms. Okay, that means when we attack C2, we have three resonant forms. When we attack C3, we have two resonant forms. That means that C2 will be more stable. And after elimination, we will get the product in C2. This is the reason why pyrrole, the most active position of pyrrole is C2 and not C3, because in C2 we have three resonance structures that stabilize the intermediate, the carbocationic intermediate, while in C3 we only have two. Then we will do exactly the same for the indole. That means if we attack C2, what we have this, we can stabilize this resonant form. Okay, we can stabilize the resonant form, moving the electrons of the aromatic ring. Okay. okay, we can have 1, 2, 3, 4, 5 resonant forms. However, if we take a little bit of attention of the resonant forms, what we can see is that in this resonant form, in this resonant form, in this resonant form, and in this resonant form, what we are doing is breaking the aromaticity of the fused benzene ring. Okay, this benzene ring is not anymore aromatic, this benzene ring is not anymore aromatic, this benzene ring is not anymore aromatic, and this benzene ring is not anymore aromatic. What implies this? Implies that we are destabilizing, we are breaking aromaticity, we are destabilizing these 4 resonant forms. That means that the weight, the contribution to the final resonant form will be almost 0. Basically, practically what means that these resonant forms didn't count. That means that we only have 1 resonant form in situ to stabilize the indole. Okay? What happens if we are doing at C3? Well, at C3 we can do exactly the same. Okay, the same that we did before. Okay, 1 resonant form, and then we can stabilize this with the nitrogen, with the pair of electrons of the nitrogen. And we get this resonant form. Don't be tempted to use the pair of electrons of the aromaticity to do more resonant form, because if you do this, what will happen is that you are breaking the octet of the nitrogen. Nitrogen is the second group, remember, the second period, remember, that cannot break the octet. That means we analyze this, both resonant forms looks okay. That means that we have 2 resonant forms for the indole. That means that for the C3 of the indole, that means that this will give us, after elimination, the final product. Why? Because it's the regiochemistry that gives us the most stable intermediate, the most stable carbocationic intermediate, because we have 2 resonant forms. Right? This is the reason why indole and pyrrole has different regiochemistry. One is C2, the other is C3. Okay? Good. Then we can go for the next one. Okay, we have these 2 compounds. And this one. And we both treat this with sodium methoxide. What we have is a substitution. Okay, and what is happening is they tell us why this one, the compound A, this one is faster than the other. Okay? First of all, we need to analyze what type of reaction we are doing. In this case, what we are doing is a nucleophilic aromatic substitution. Okay? And if you remember how it works, Basically, the nucleophile, that is the methoxide. Remember, methoxide is a base, but also is a very good nucleophile. What is happening is attacking where we have the future leaving group. Okay, we generate this intermediate. Okay, that we can stabilize. This is the Wheeler intermediate that we can stabilize. Okay, doing this. Okay, and then we can stabilize this negative charge going here and get okay, that means that we have three resonant forms. Next, the last step is basically the elimination to form the final compound. If we do exactly the same in the second compound, we get a very similar okay, we got this, and then in this case we can think that maybe we have this, but this is because the sulfur can expand the octet, but as I explained a lot of times, even if we can stabilize the octet, even if the octet, we can expand the octet, this resonant form is not very good, because remember the overlapping, especially in orbitals p, between a sulfur and a carbon that are from different periods, it's very bad overlapping. That means that doesn't come out. But anyway, we have this, sorry. That means we have two resonant forms here, we have three resonant forms here. That means that this will be more stable, means will work better, means will be faster. Okay? Then, when we are analyzing D, we have 8 peaks. Okay, this is another. The second question is we analyze the spectra of D. And we see in the 13 carbon 8 peaks. Why? Well, remember that the carbon is always decoupled with the fluorine, with the hydrogen. That means that the only that we will see is the coupling of fluorine. That means this carbon will couple with this carbon will couple with the fluorine, this carbon will couple with the fluorine, and this carbon will couple with the fluorine. That means that we have 1, 2, 3, 4 different carbons, and each one is coupling with the fluorine. That means that what we will have is 4 doublets. That means 8 signals. Yeah? One question that you can ask me, why the carbon is not coupling by the other carbon? Why this carbon is not coupling with this carbon? Well, remember that the carbon 13 is not the major isotope in nature. We have, I guess, that is around 0.01. That means, simply, if we have a carbon 13 here, the possibility that we have another carbon 13 here in the same molecule is very low. We don't see these couplings. Okay? Then, they say that if we see E, if we see D, we we only see 5 peaks. This compound, and now we see 5 peaks. Okay, we don't have fluorine, that means that the carbons are not coupling with fluorine, and how many carbons we have? 1, 2, 3, 4, plus the methoxide, 5. 5 carbons, no couplings, 5 signals. Okay? Always think that the carbon normally is coupling with fluorine. If we have a fluorine, it's coupling with fluorine. Carbon-carbon is never coupling together. And then normally, when we are doing a carbon NMR, we are decoupling from the hydrogen. Okay? Good. Go for the last exercise. Dun, 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 dun. Okay, designing a synthesis of the following molecule. From okay, well, basically what we need to do is first try to think how we can build this compound. Okay, this is a pyrrole. I only teach you 2 ways to form a pyrrole. Basically, one is from 1,4-bicarbonyl compound, 1, 2, 3, 4 carbonyl compound, or from an amino ketoester. Obviously, this is a Paul-Knorr synthesis. Why? Because in the Knorr synthesis, what we need is an electron withdrawing group here, that we have in this case, but also here, that we don't have. And the starting material is a 1,4-bicarbonyl compound. That means probably not, by sure, this will come from a Paul-Knorr synthesis. However, if we do a Paul-Knorr synthesis of this compound, something is missing. This is missing. But can we synthesize this after forming the pyrrole? Yes, it's very easy, because this is we can do this by electrophilic aromatic substitution. That means that this can come from here. And if we have this compound, if we want to have this compound, this is a direct Paul-Knorr synthesis from this compound. That means we can start a forward synthesis with this compound. We add ammonia. Remember that this was a little acidic. What we will get if first is the hemiaminal, which one is protonated, and we eliminate the water to form the fercimine. Remember that all of this is in equilibrium. When we have the fercimine, tautomerization to enamine, and then intramolecular attack, we protonate this to make more active this position, more electrophilic. Intramolecular attack, to form again the hemiaminal, okay, and then again we protonate the hemiaminal, we protonate the wedge to make water, that is a very good leaving group, and then water is eliminating, And here you have two options. You can eliminate directly this hydrogen, that I guess is what I did in the last exercise. But also we can do the imine without any problem. And then if we have the imine tautomerization, imine enamine, to form the final compound that we want. And remember that this is the last irreversible step. All the others are equilibria. Okay? Then, when we have this compound, we need to put the ketone. This is basically, we can do it with a Freirel-Crafts acylation. We can start with acetic anhydride plus, for example, indium trichloride. Okay? If remember that this is electron-rich ring, that means that the electrophilic aromatic substitution is working very fast. We can use very soft reagents, but if you don't remember how to do it, you don't remember indium chloride, you don't remember acetyl anhydride, you can use always the acyl chloride and aluminum chloride. Okay? In real life, I will not recommend it. Pyrroles are very sensitive, that means you will have a lot of side reactions, but on the paper, everything works. Okay? That means this is how we can synthesize this pyrrole from a 1,4-D carbonyl compound. Okay? Remember that the formation of pyrroles, basically, we only know two systems. One is the PAL-NOR from 1,4-D carbonyl compound, and the other is the NOR synthesis from amino ketoester. Okay? Remember, it's very important that you know how to synthesize these compounds. I repeat it a lot of times, but these compounds can be synthesized very easily by Umpolum reagents, basically DTNs. Okay? Check Bruno notes in order to do this compound. Okay, then we go for the last one. We need to synthesize this compound from this one. Well, we have another pyrrole. How we can know if we have to use a PAL-NOR synthesis or NOR synthesis? Well, basically, remember, if we have an electron withdrawing group in the 2 and 4 positions, like we have here, the possibilities that we are doing a PAL-NOR synthesis, a NOR synthesis, is very, very high. And what we need? Remember, what we need is, we can break this bond, we can break this bond, and what we have is that this bond, what we have is that what we need is these two starting materials, the ketoester and the amino ketoester. How we can synthesize it? Well, this is very easy. From here, basically, what we need to do is a Claisen condensation. We take this compound, we add sodium methoxide, and we form a negative charge here that attacks another molecule of the ester, addition, elimination, and we generate, after HCl,